Now the last problem that we're going to look at in this chapter has to do with a regression problem again, only this time we're going to talk about a logistic regression equation. It's kind of a special type of equation in that you can't just continuously have exponential growth for certain things. Like if we wanted to talk about the population, for example, there is going to be a point where we are not going to continue to grow anymore. And a logistic regression kind of combines a couple of equations together, and it accounts for the fact that we are going to max out at some point. And we have this logistic regression equation automatically built into our graphing calculator. So that's what we're going to kind of look at for right now. So here we have a table for the world population. It's given in billions for 7 selected years ranging from 1950 through 2010. So these are the years after 1949 and their associated populations. So we're going to take this information in the table right here and we're going to put it in the graphing calculator. So I already have that done, and again we're going to let x, which is our independent, be L1 and our y be L2. So in the graphing calculator you're going to put both of those lists in. If you need to pause the video to do that, go for it right now. I have already done that. I've already got my lists put in, and remember that we get to it by going to Stat, Edit, and my L1 and L2 are already in here. If you forgot and you already had lists in your L1 or L2, don't forget, I guess, that you can arrow up and you hit clear to get rid of any data that was already there. So since my data is already in there, I can choose a window for this. I'm not being specifically asked to graph it, but it is kind of a good thing to maybe check your equation to the points that you're plotting. So we're going to go ahead and put it in a graphing, and we're going to graph it anyway. Okay, so the window that I'm going to choose is based again on my x values that come from L1 and the y values that come from L2. So the window that I chose has an x min of 0, an x max of 70 with a scale of 5, and a y min of 0, a y max of 10 with a scale of 1. And again, I got my x's and my y's from the table that we had listed right here. So if I go in, and that's kind of a starting point, sometimes you might have to adjust it, but I didn't have to in this particular case. Okay, you can see that I already have my equation for us listed there. I mean, it's already obviously on the y1 because my line is passing straight through it, but my dots kind of look like they're almost in a linear form, but they're not, because we're told we want to use the logistic regression equation. So, okay, I had to take off my line because I'm going to repeat the equation in there. Remember that when we're going to do a regression, we go to Stat, we arrow over to Calc, and I can tell you that my logistic regression equation is down towards the bottom of the list. So I'm going to just arrow up, and there it is. It's option number B. So that's the one that I'm going to choose, and I hit enter. That's logistic. So I want to store the regression equation on my y1. I can do that by hitting alpha F4 and choosing y1. And now I want it to calculate it. And it's this equation that the calculator is coming up with that I actually want to save. So it's going to spit it out here to us any moment. Alright, so I have the equation. I'm going to pull it off over here to the side and keep it for a second. But I want to go back to my graph. Now that I put that equation on the y1, you can see that it's creating the function, or it's graphing the line that is that comes from the equation that we just made up, and it's pretty dead on. You can kind of see that right there. So that means that I would assume that this is a very good function if it matches up those points that well. So we're going to come over here and we're going to look at the model that we've got. And I'm going to make this a little smaller so that you can see it a little bit better. Now, how do I write this equation based on what is given to me from the calculator screen there. It says that my logistic equation looks something like y equals, the numerator is going to be whatever c is. So c is we'll call it 12.57. And that's divided by 1 plus a, which in this case is 4.11, times e raised to the negative b, which is 0.026, we'll call it negative 0.026 times the variable x. This function right here is written in some form that we can kind of recognize it as, and this is a logistic equation, and it models this growth that eventually is going to cap out. Now the second part of my question says, well, how well does that function model the data that's being shown from the table? In other words, the model that we calculated is only a prediction, and models don't have to be correct all of the time. They might overpredict or they might underpredict. This information that's in the table is real hard data. It is true that in the year 2010 there were 6.9 billion, I think, people. Now, how well does the model, how close does my model come then to these numbers that are right here? Easy way to do that is to take this value for x and plug it into the table in my calculator. Because my equation already exists in the y equals, all I have to do is go to second table, and I am going to get rid of that so that you can watch me do it better, and we'll do it again. So I want to delete that value, and whenever I want to let the calculator evaluate an expression for x, I can do it from the table since the equation's already in my calculator. So I'm just going to let x be equal to 61, and I want it to tell me what y is. It tells me that y is 6.9, so we're going to pull that down so we can see it as well. So it was a pretty dead-on model. The real data is for 61, which remember was 61 years after what, 1949? 61 years after 1949, the actual population of the world, world population was 6.9 billion. Our model said 61 years after that, your world population should be 6.92. So that's a pretty close model. I want you to understand that when we create these regressions based on, so we're creating an equation or a model based on data like this, that the models don't always match up perfectly with what we've got, because again, their theory, they're just an algebraic expression or an algebraic problem, whereas this is the real world and this is what's really coming out of that. But we do use models to be able to predict, and that's the important part.